Thank you, and thank you to the organizers. It's because I've spent so much time in Tsinghua and Tokyo, it's lovely to be here and to see people meeting from both places, both junior and not so junior, and so I'm grateful. Now,
can people at the back hear what he says? Oh, okay, great.
Great.
It's okay.
Great. So I'll work in a similar setting to Yukade's talk, always taking F, a crepant resolution. So a map from X smooth to Y, and this taken to be crepant, which means that the canonical on Y pulls back to the canonical on X. So I invite you to think of this as a relative Calabi-Yau condition. So I got the name of the workshop in early, in the sense that, of course, if this is trivial, I'm requiring that this is trivial. So if I start with, for instance, the singular Calabi-Yau, then X is going to have that property, at least triviality of the canonical bundle. And so the first example for my talk to think of is, as earlier, we take this A1 surface singularity. So picture this as a cone with this singular point, and we may, just by blowing up that point, get a smooth X. And let me draw this as follows. What we've done is inserted an exceptional locus E. So this E is just a projective line, a Riemann sphere for working over C, and we can think of working over C. But my interest in these resolutions is slightly different. It's to take dx. So this would be the bounded coherent derived category. And I'm interested in the symmetries of this. Okay, and I mean, so this we can relate to topological B-branes in the string theory on X. So I'm, in some sense, also studying those. And so when I say derived symmetry, I mean a symmetry of this category such as the following. So let's write T, and it's going to take the structure sheaf on the exceptional locus, so considered as a coherent sheaf on X, and it's going to shift it. Okay. So this derived category is built out of chain complexes of coherent sheaves. So I'm taking a sheaf in degree 0 and pushing it up to degree 1. Okay, so such a symmetry exists, and I'll describe it, at least briefly, later. Why am I interested? Well, a bunch of reasons. So to position these in relation to things that might be more familiar, if I consider the Grothendieck group on X, so this is just vector bundles on X. So the abelian group generated by them up to some equivalence relation, given when I take a short exact sequence of vector bundles, that extension of two vector bundles I convert into the relation that the extension is A plus B, the two things I'm extending. Okay, so this is just an abelian group, and what does this correspond to? This T, well, let me write TK for the corresponding thing. It's simply a reflection in the class of this object OE, right? So why is that? Well, if this is shifting OE by -1 on this K group, it's just replacing this by minus, according to that relation I just briefly explained. So you can think of this as categorifying a reflection on K theory, if you like to categorify things. So other applications that I won't talk about, but to place this somewhere. So, well, of course, we might just be interested in the automorphisms of this category. We might be interested in mirror symmetry. So, in that case, this T would correspond to a Dane twist of some sort on the other side of the mirror. We might be interested in Bridgeland stability on X. So in that case, if we had a Bridgeland stability condition, applying this T would give us a new one. So it lets us move around the manifold of Bridgeland stabilities. Yeah, and I mean, typically you describe some patch on that manifold, and then you use these symmetries to translate that patch. Okay, and then it also this is relevant to enumerative geometry. So you can use such things, for instance, to understand Gopakuma-Vafa invariance in work of Toda. Okay, so that's some orientation, I hope. I'm thinking of X. Well, in this case, it's a non-compact K3 surface, but I'd also like to think about Calabi-Yau threefolds and beyond. A note also that this example is quasi-projective, but it's not a problem to work in the projective setting in what I'm going to say. Okay. So that's something about the setting. Now let me give some general motivation for what I'm going to try to build. And that will be a generalization of this T. So a remark that so in a setting that was discussed in the last talk, and many people will be familiar with, if I take F, now I'm thinking of a threefold or higher. So, and I have what's called a flopping contraction. So, let me draw this out. So at the bottom of the board, I think there's going to be a conjecture that if I have F a flopping contraction, then, as we were saying before, you have the other side of the flop, X prime, some new threefold or higher, in which the exceptional locus E of this contraction is replaced by something else. Yeah, this process is also preserving the Calabi-Yau condition. So it's conjectured that if I have such a setting, I mean, I should write flop here. So we have a flop that for any dimension, then we should have equivalences so f and f prime, say, associated to this diagram going between x and x prime. Okay. So this would be the last bit of motivation. So it's a corollary of this conjecture. This conjecture, which is very open in higher dimensions, that have symmetry, let's call it TF, given by composing these equivalences. I'm putting an inverse there just for conventions later. And so this is non-trivial in known cases. So putting this together, given such a flopping contraction, we conjecture that there exists a symmetry associated to it. So we would like to describe this. So let's say just how to describe. So I'll try and make some progress towards that in this talk in some general setting. And this is interesting because this conjecture is very hard. But you might hope that describing the corollary, the symmetry in this corollary might be easier, because after all, we only have to work on 1x. Yeah, but this is expected to be hard in general. But we seek a general approach. And why is that hard? Well, in a word, because the exceptional locus, this this example does not show this fact, but in this generality, the exceptional locus of this contraction is very complicated. So it's maybe generically a fibration, but it's stratified. It has fibers P1 and Grassmannian's homogeneous spaces. So yeah, if we can describe this, I think it's worthwhile. So if there's no questions on that introduction, I will state my setup, and then I'll remove the mystery about what that T is in such a way that we can generalize as follows. Okay, so once again, we take a crepant F, and so that's from X to Y, and I'm thinking of Y always as a singularity, and F as a resolution, and I'm making Y a hypersurface in some S, which I require for simplicity to be smooth. So it probably suffices for this Y just to be a hypersurface singularity, and S smooth in a neighborhood of Y in this setup. But let me put those assumptions for simplicity. And let me control the geometry of F in the following way. Let me make F the blow-up in some locus A. So this locus A. And let me, again, for simplicity, ask for A to be smooth. That can be weakened. Let me take it to be of constant codimension n. So in a moment I'll introduce an example or a family of examples that we'll come back to. But just for notation, let me say if you blow up A in Y, then you get the exceptional locus in X, and let me make that fiber over A by P. Okay. And so then an example. So this is in a family where this codimension n starts at 2 and grows as follows. I take Y to be, can we see there? Yes. To be the cone given by a homogeneous polynomial of degree n in n plus 1 variables. So yes, yes, I've been careful with that, I hope. Okay, so this is a cone in affine n plus 1 space, and I blow up just the vertex of that cone. So, oh, speaking of blow-ups. Okay, so this is my setting, and I mean, for you that are starting to imagine this is quite nice because I can and will calculate this this blow up just by reference to the blow up of 0 in the ambient affine space. So let me come back to that later. But first to describe this T. So let's take a general setting that will fit this T and the thing I want to introduce. So take a functor to the derived category X from C. So this is, well, just another DG category I'm thinking of. And take R, the right, A right adjoint for this. And then we may attempt to form the following functor acting on dx. I'm going to call it TF. This is going to recover this T. This is called a twist because it's mirror to a Dane twist. And what property do I want it to have? Well, I want it to take an object of dx. I mean, so first think of a coherent sheaf A, and I want to replace it with the following. So associated to this adjunction, I have a co-unit, natural, what are they called? These are functors and these are natural transformations, yes. A natural transformation like this. And you might hope that after applying the right adjoint in F, you still have a coherent sheaf. So if so, what I want to take is simply this complex where that coherent sheaf maps to the one I started with via the co-unit. So more generally, A might be a complex of coherent sheaves, so I have to do some other construction called the cone to get this new object in dx. But anyway, we get this TF, and we can hope that it's a symmetry. And the formalism to see whether it is as follows. F is spherical if TF is an equivalence and also some dual construction. This is just given by taking the unit here rather than the co-unit, so let me not write it out at this point. I also want the co-twist CF to be an equivalence. So this is one of a bunch of equivalent definitions of spherical, but in particular I'm claiming that TF is an equivalence. So I'll show you how at least this is consistent. So this is in the original formulation Seidel-Thomas, and in this formulation it's Anno and Anno Logvidenko. Okay. So this is abstract, but let me relate it back to our example. In fact, this will encompass this family of examples. So I take my F to be simply the following from the derived category of k-modules. Let me write it like that, to dx. So the functor which is specified by taking the rank 1 k-module to OE. So this is spherical. Okay, so let me indicate why that is from the definition. So first, TF, and I'll write this as TOE. Takes A, and it forms this thing I've written here. What's the right adjoint to this functor to dx? Well, the right adjoint is given by taking HOMS from OE. And so then that can be thought of as a k-module, or a complex of k-modules. I should say that functor's derived. And then from that k-module, I want to get an object in dx. I do that simply by tensoring with OE. Again, it's a derived tensor. So we have an object like this, in general a cone built like this, and the co-unit is the evaluation morphism, like evaluating HOMS from OE to the object A. Okay, so I've now constructed the T that I started with. This is the symmetry that I was seeking. And what about the co-twist? So note CF. So as I said, it's just given by the cone on the unit instead of the co-unit. And so what's that? Well, at least applied to K, it will be the following. So I think you can believe this is the dual thing, the co-evaluation. Okay. So we take HOMS from OE to itself. These are both calculated on X. And if you take that X and you calculate the HOMS from OE to itself, you'll get a copy of the field. But this notation includes a derived functor X, so you also get some self-X2, which will be set dual to the HOM. And so in sum, you get the cohomology of a sphere of the same dimension as X. Okay, so sphere. This is why we call these things spherical. So this just has cohomology in 2 degrees. when I take the co-evaluation from K and take cohomology, that just leaves me with cohomology in 1 degree. Okay. So the result is a copy of the field shifted by the dimension of x. So we get that CF is an equivalence. Okay. So this is the check that F is spherical in that case. Okay. And I go through this because I'm going to introduce a new F in the setup, which I hope will answer some of our questions. Okay, so I state the theorem. So for technical reasons, I said D was the bounded derived category of coherent sheaves. DB co. I'm going to take objects in that which have compact support. Experts will suspect that this is because I need a Serre functor for some of what I'm going to say, and that's indeed the case. Okay, so the first theorem is that given the setup, which we'll keep throughout, then the pullback along, need to write it in. Call this composition G. The pullback along G is spherical. Okay, and as before, I mean the derived pullback. So I claim this is a spherical functor, and by definition, therefore, I claim that it has a twist that gives an equivalence, which acts as a derived symmetry on X. Okay, so that should be related to the T I started with, and indeed it is. So let me explain now the relation, how to describe that symmetry. So theorem A, because example A is the canonical example, where taking n to be the codimension of what we blow up, so this theorem works for codimension 1 or more, right? So codimension 1, you might think it's boring because then you're blowing up a divisor, but actually there are interesting examples where you're blowing up a non-Cartier divisor. So let me get onto that. But for n equals 1, we don't need an extra requirement, but for n greater than 1, we require not relative Calabi-Yau, but absolute Calabi-Yau. Okay. So I could have just said Calabi-Yau generally at the beginning, but I'm interested in the relative Calabi-Yau case for various reasons. These results are nice because they work smoothly in families. I mean, they work easily in families, and we were aiming to do things in higher dimensions, so that's nice. Okay, so theorem A continues. We have some further spherical functors, and these are going to describe the twist of G star. So bear with me while I write these out. So for those who have worked in this area, these will be somewhat familiar, but also in this generality new, I think. Okay, so I claim this is spherical. So what is this? Well, this is just a natural functor associated to the blow up that I've done. Okay, so I start in DA, the blow up locus. I mean, in the example, that's just a point. I pull up to the exceptional locus of the blow up, and then I have these tautological line bundles coming from the blow up that I can twist by. So I do that to some degree, and then I include into X. So this final function is just pushed forward into X. So for instance, in the example G1, where this is not doing anything, obviously here, G1 is just recovering that F. Okay, so this is a slight elaboration of the example, which will work in generality. Okay, and then 2, which for me is the meat of the theorem, is describing this symmetry, the twist by twist of G star, or its inverse more conveniently. So this will be the twists of the GIs and then a contribution from the normal bundle of X, and then a shift. Okay, so this is the normal of X, and the normal where? The normal in the blow up of the ambient. Okay. So we have this new symmetry, left-hand side, and we have a description of it, which was totally new to me, at least. Okay, so some remarks, and then a bit of proof. So clearly, if I rearrange this, I have, for instance, this symmetry. This combination is just written in terms of the TGs. So in particular, it's independent of that embedding in S. So, and right. So if we just started in our original setting with a contraction F, and then that's nice because it's independent of this extra smoothing that we introduced. Okay. So, so this example I started with, let me now spell out the theorem in this case. Okay. All right. That's quite a workout. Yeah. Yeah, would you mind cleaning this board? Oh, thank you, thank you. Yeah. Okay, so example A, just for n equals 2, what have we got? We've got a quadric cone. So quadric in 3 variables y, and so of course we have an embedding of this in K3, and what I was doing is blowing up the origin A, so just blowing up a point. Let's write it like this. Yeah. And so the blow up introduces a P2 like so, and I can then calculate the blow up of A and Y as the proper transform of that, and we see the exceptional locus of that blow up appearing as a conic P1. Right? Okay, and so then E is that conic P1 embedded in, like so. Okay, and then the result is saying that we have this new twist, which is associated to just starting with the affine space and pulling back all the way to here via the resolution, and that it's given by, in this case, 2 factors. So in that notation, the twists associated to OE and the twist associated to OE2. And then we have the twist by the normal bundle. That, in this case, is O4, pulled up from the P1. Where's that 4 coming from? It's just the self-intersection of the exceptional locus in P2. Okay. And then there's a homological shift. Okay, so that's the result. So we have this new, very simple thing and a formula for it. And yeah, this was quite new to me. So it's easy to see if you know the calculations that this thing fixes this special sheaf on the exceptional locus. Why? Because this twist includes a push down via G star. So in particular, if you have OE minus 1 here and you push it down, you get no cohomology. So this fixes that. Less obviously, this combination fixes this OE minus 1. So it jumps the minus 1 up to 3, and then these jump it down to 1 and back to minus 1. So yeah, and we claim this in more generality. I mean, so for instance, if n equals 3, then E is a cubic surface, and so on. Okay. Right. So let me check for time. So about 20 minutes. Let me say a word about the proof. I won't give many details. So it's the proof of theorem A, and it includes the first theorem. So from the setup, we have x to y in the smoothing, and we're interested in G here. I also have the blow up of A in the smoothing, and because this is a hypersurface, this inclusion is also a hypersurface. So it's easy to check, just using the causal resolution, that the following f, so there's a different f now, is spherical. When I just restrict from BLAS, so I restrict from BLAS to X. So this is a very general property. If I have a Cartier divisor, the causal resolution means that this functor satisfies those conditions. And this is the key because this blow up, this is no longer a crepant morphism. We've changed the canonical bundle, and we have, how to write, a decomposition of this derived category in terms of S that we started with and the locus A that we blew up. So we have a bunch of copies of A. How many do we have? Well, A is codimension n in Y, therefore it's codimension n plus 1 in S. Therefore I have n copies. And what's this got to do with the statement of the theorem? So if I take this functor f, which is defined on the whole blown up category, and I restrict it to each of these pieces, then by design it gives me those functors. Okay, so the first one is easy. So what do I want? I want pullback along here restricted to this subcategory of here, which is pulled up from S. Okay, so it's just pull up, and the composition then is G star. Right? So that's the first restriction. And GI are engineered to be the restrictions of the remaining categories. So this is G1 to Gn that we get here. And so that's a little hard to see. You have to draw a natural, like 3D commutative diagram that extends this in naturally coming from the blow-ups of A and Y and A and S. But once you've seen it, it's quite clear, I think. It needs a base change. The smoothness of this. So that's why we need S smooth, at least in some neighborhood. That, again, may be possible to lift that, but I've not worked out the technicalities of that. Okay, but then what's the punchline? That TF, this spherical functor here, is, again, this is a part of the causal resolution, is the normal bundle of X, or the conormal bundle of X, shifted by 2, and then this functor factors using F crepant. So I'm hiding quite a lot in there. But the point is, Halpern, Leisner, and Shipman, and in a different setting, Addington, Aspinwall, have these general criteria for when you have some spherical functor from semi-orthogonally decomposable derived category, how the twist of it will factor. Okay, so that's giving us that this twist by this conormal bundle factors into TG star, TG1 up to TGN. So that's where the result's coming from, and each of these come with conditions involving this semi-orthogonal decomposition and the dual one. They have to interact in some way, and crepancy is precisely what gives that. Okay, so this is for n equals 1, and this is for the general case. Okay, so have 15 minutes, and yeah, I can come back to the case n equals 1. So we worked in this generality, but n equals 1 turns out to be the case of interest for threefolds. So like this family of examples starts with a surface. It's generalizing that, but I'll now show a family, well, or at least an example on a threefold. I'm not sure if we'll have time to generalize much, but I'll at least state the theorem. Okay, so this can probably all go. Okay, so we're now in the case n equals 1. So then A is a divisor, and if this is going to be interesting, then it better be a non-Cartier divisor. If it was Cartier, this F blow up would be an isomorphism. I mean, we'd still get something in that case, in the sense that this pullback by G would just collapse to the pullback along this hypersurface, and that would be spherical. But it's not interesting. So example B then is the following. We start with Y, the conifold. So that embeds in K4 this quadric, and I make a small resolution of it by blowing it up in a choice of non-Cartier divisor. So we can do this just by partitioning the coordinates 2 by 2. So if I take this divisor, then what happens, if you've not seen this, is that this is Cartier all except at the origin. So yeah, notice this is a cone, now 3-dimensional. And blowing up this divisor here gives a small resolution of this singular point here. So what do we get? An X again. And the exceptional locus of that blow up. Okay, so this is not the exceptional locus of the small resolution, right? Because we've blown up this divisor. So what it is this divisor. Notice in this example it's just the plane K2, whereas this would be the blow up of K2 in a point. Okay. So this divisor of the plane, as we've blown it up, just has a P1 introduced in it. Okay, so this is still P, and note that P is then the blow up of some locus B, so a second blow up locus, where B is just a point. Okay, so that sets us up for theorem B, and this is proved by a dual technique. And what it's going to do is give us, in this case, n equals 1, and I want P to be the blow up of B, where B is smooth codimension 2, as in this example. It's going to give us a description of TG star. Okay, and I also want some compatibility between the two blowups. So associated to P, I have twisting sheaf OP1, and I want this, well, to restrict to the twisting sheaf for this blowup. Okay, so this is a bit hard to compute, but it's necessary. So I just want this to be degree 1 on the fibers of B. Okay. And then I have the following, and it's similar to theorem A, but B has a different role to A, right? So B is the second blow-up. So from B, I pull up to the exceptional locus of B in A. Let me write out what that is here. So, so the exceptional locus of the blow-up of B in A is, that's this P1 in that blow-up there. So in this example, we're just pulling up to that P1, we're twisting by O minus 1, and then we're including into X. So I claim this is spherical. So this is an elaborate way of saying this, but this is a spherical functor that's familiar on the conifold. It's written this way for generalization. Okay, and then the result is the following, that TG star, so we've no longer got the inverse because a dual's appeared, with some shift, and tensor by the following. Right, so the bundle associated to that divisor Y, but restricted to Y. So we can pull it up to X. If you like the notion, this is the relative canonical of G. So this is TH. Okay. Right, and yeah, like just a word on the proof. So this is using similarly a spherical functor from DEAY to check I've got this right. Yes, to DX. Okay. So I was claiming that the pullback along a divisor is a Cartier divisor is spherical. So this is the dual thing, that the push forward from a Cartier divisor is spherical. And this is the blow up of B in A. So we can play the same game, get the factorization, and this is it. Okay. Right, so to finish up, some notes, how this fits in. So for example B, long time ago proved this result with Segal by a different method. So using grade restriction windows. And yeah, what's interesting to me about this is that, oh, to be clear, theorem B is also like using theorem A. Right? You use theorem A for the first factorization, and then this is the refinement coming from this. So it's that this somewhat old result fits into this much bigger picture. And also, let me not explain what they do, but more recently Bodzenta and Bondal work in a different generality. So this is a flopping contraction of a curve. They work for a family of curves, and like they allow certain degeneracies, and they nearly get this result. I think there are some categorical technicalities which mean that they don't state it quite like this, but they essentially can show this. And this, I think, provides an alternative way to think about that. All right, so to finish, I guess, let me state, maybe here I'll lose this proof. State what this is saying in example B. So first note that the LHS there of 2 is independent of the embedding. So let's calculate it for example B. So in this case, the B that I blow up is just a point, and the exceptional locus of blow up a B in A is the P1, which is the exceptional locus in this small resolution. Yeah. Okay, so yeah, we could then, using that notation, theorem B is saying, well, here that omega g is just trivial because we're in an affine case. So it's saying that T g star minus 2 is the twist by OE minus 1. Okay, so note then that the same left-hand side recovers the TF that I defined earlier. So remember that was when I have a flopping contraction, the flop. So in this case, the flop is given by this. So it's interesting to ask what happens in other examples. Okay, let me see how I'm doing for time. Okay, a couple of minutes. So I could quickly then state a generality in which this works. And it's a bit backwards, but these are the examples I first tried to cover. So right. All right. So this is some family of that threefold example. So the setting, let me go a bit quickly. So you take S, the ambient smooth manifold, should be a rank 2 vector bundle given by F over A. Remember, that's the locus we're going to blow up. And I take a section of the dual of that. What's nice about such a section, it gives me a function on the total space of S. So then my setup is going to be the following. I have A, the 0 section, 0 section of S, and in that total space I can define y as the vanishing of that function. And then I have B, which is the vanishing of the section. Okay. So this is on the one hand recovering example B. How? I just take a trivial rank 2 vector bundle over A2, and I let the section be, what were my coordinates? Okay, I let the section be, let's write AB for the coordinates on A2. So it's the tautological section. Okay, so that's recovering example B, and yeah, sorry, I'm a minute over time, but this pretty example. If I then instead take OP3 minus 2, okay, so my smoothing will be the total space of this vector bundle, 2 copies of OP3 minus 2, so that's over P3. And I take a generic section of the dual of that. That's degree 2, 2 in P3. So B is an elliptic curve in P3, and we get, well, it's fun to draw. So if this is my B, the elliptic curve, then what do I have? This is in P3, and then my Y is a fourfold. So generically this section has rank 1, therefore it's cutting, this Y is cutting a sort of line out of each fiber, but over the elliptic curve it's cutting a whole fiber out. Okay, so we have these singularities. So Y is then a fourfold with an elliptic curve's worth of singularities. We resolve that just by blowing up the P3, and theorem B applies to this setting. So sorry, it's a good point to stop. Thank you very much.
To find a spherical quanta, only commutative thing is enough to find spherical things, right?
Yes.
So is there any reason why? So we don't need any non-collisive information mastery.
Yeah. Okay. So to say some background to that, so there exists a generalization of this when we have a general threefold flopping contraction, which involves non-commutative deformations of the analog of this object. So I don't know when that setup and this setup intersect. So I think that for any -3,1 curve, A is not smooth. Note for -2,0 curve, it is smooth. I mean, you can just take it to be a plane. So that's an example to try. I didn't actually try yet. For a -3,1 curve, I think it's not smooth. The question, at least for my current proof, is whether it's LCI in S. I fear it's not, but it's easy to check, especially with magma or something. But yeah, I mean, I suspect that some version of this must work, and then what is TG star? I don't know. Maybe it's the non-commutative twist, maybe it's the fiber twist. I also talked to Michael Weems and he doesn't know. So that's exciting.
I have a trivial question. That you have case 1 n is equal to 1.
Yes.
At the case n equal to 4, and you put condition requirement when n is larger than 1, n
Yes.
is 0, 1, 0,
Yes.
8. So in 0 B case, you put some other conditions if you consider n equal to or larger than 1.
So can I interpret it as can I generalize theorem B to n greater than 1? So on the face of it, no, because let's see, for n equals 1, this, what's the point? The generic fiber dimension of this is 1. Whereas for higher n, the generic fiber dimension is, the generic fiber dimension here is 0. For n greater than 1, it's positive. So it can't be a blow up in this way, but I would like, when the geometry is more complicated, to be able to make a analogous statement, but I don't know what it is. Sorry, that's not a very satisfying answer.
Any other comment?